This last video in our collection is going to give an example of how we can apply our newfound knowledge of partial derivatives to data science and to lines of best fit. So the example I'd like to look at is when we have a collection of values, we're going to denote our inputs by this set X, where the elements of X are enumerated from 1 to capital N. And similarly, our outputs will be denoted by this set capital Y, enumerated Y sub I from 1 to N. And our goal when we're trying to create the line of best fit for a set of inputs and outputs is to come up with a line where we'll plug in an X value as our input and get a predicted Y value as an output. And so what we could do for each of the Xi's in our input set is we could compare the actual outputs to the predicted outputs via the residual sum of squares. So that's the example that I want us to think about. And prior to this, I've given you the equation for finding the M and the B values for this line of best fit. And they seem like totally crazy formulas, and you've got to look at them and wonder, where on earth did those formulas come from? And they actually come from looking at partial derivatives. Now there's a little bit of a change in mentality that we're going to have here. Normally we think of X and Y as our variables in an equation. And ultimately we're going to get to a place where M is constant and B is constant. But at this moment in time, we're trying to figure out the M value that we should use and the B value we should use. So right now, we want to think of M and B actually as our variables and think about the fact that the input values that we're given are something that we're not allowed to change at will or control. Similarly, for those actual output values, they are what they are, and then we shouldn't think of them as like a variable that we're able to change. So those sets are things that we're not allowed to tamper with. Additionally, we're trying to create a line of best fit right now, and so the fact that we need to have a predicted output that looks like a line is also something that we won't be changing. So the only two things we really can change are going to be the M and the B value to fit this situation. So we're going to be thinking of the letters M and B as our variables here. Remembering back to what that residual sum of squares function is, if we now think of that residual sum of squares as a function of the variables M and B that I've color-coded to match with our previous examples, we have that this function, as a function of M and B, is given by this equation. Each one of these little individual Y sub I actual outputs minus predicted outputs, Mx sub I plus B. We take that quantity and square it so that we don't have to worry about any negative values. Then we sum up all of those residuals that are squared to get our residual sum of squares model. Now we're about to dive in to taking some partial derivatives of some messy looking functions. So the algebra is coming in the next set of slides, and it's going to get a little bit intense. Take a deep breath. As we go through the rest of the slides, don't beat yourself up over trying to memorize every little detail, but try to go through them appreciating the spirit of what we're doing and just how much we're able to accomplish with this new technique. So one last deep breath, and let's dig in on the algebra. All right, before we jump into the messy equation with the big summation in it, I want to take a look at an individual residual here. One specific actual output minus a predicted output, that quantity squared. And what I'd like to do is consider the partial derivatives of this individual residual with respect to M and with respect to B. Looking at this individual residual, let's first apply the chain rule. When we're treating M as the variable, we think of the B as just some other constant right now. So we use our chain rule to bring our 2 down in front of this quantity. We leave the inside of the parentheses alone and subtract 1 from the exponent for a 2 times the quantity y minus mx plus b raised to the first power. But we are using the chain rule, so we need to multiply by the derivative with respect to m of this inside, and the derivative with respect to m of this inside is going to be just the coefficient minus x right here. And when we distribute that minus x to each of the terms on the inside here, this is what we're left with as the partial derivative of a single residual with respect to the variable m. The process is almost identical when we switch to the other partial derivative, but this time we're viewing b as the variable and m like a constant. We apply our chain rule, bringing the 2 down to the front, leaving the inside alone, subtracting 1 from the exponent, and multiplying by the partial derivative of this inside expression with respect to b. And here, that will just be the coefficient on the b, which is a -1. Distributing that -1 and the 2 to each of the components here, we arrive at this expression for the partial derivative of a single residual with respect to b, just slightly different than the partial derivative of this residual with respect to m. Next, let's use the fact that partial derivatives respect addition. When we were looking at our residual sum of squares, we were adding up a whole bunch of these individual residuals. We just took a partial derivative of an individual residual, but partial derivatives play nice. So if we want to know the partial derivative of the sum of all of these residuals, it's just the sum of the partial derivatives. So altogether, the only difference from what's right here and what's right here is I've put the big scary sigma in front to add up all of the things that look like this for various x sub i's and y sub i's. And similarly with that second equation. So that's going from there to there. Just add the sum in front and subscript your x and your y's for each individual residual. So overall, finding these partial derivatives, not super pleasant, but not so bad. In a single variable calculus setting, we find the extrema of our function by taking the derivative of our function and setting that equal to 0. If we want to find all of the extrema of a multivariable function, we're just going to repeat that process. Instead of setting one partial derivative equal to 0, we're going to look at our collection of partial derivatives and set all of them equal to 0. And instead of having a single equation set equal to 0 that we need to solve, we will then have a system of equations all set equal to 0, and we need to overall solve this system of equations to know when we've found an extrema value. We're looking for an extrema value of our residual sum of squares function with respect to our variables m and b, so that hopefully we can find a minimum of that residual sum of squares function to find the line of best fit, in other words, the line that has the smallest possible error measure for our situation. So let's do that. Let's take our equations from the previous slide, those partial derivatives that we found with respect to m and b, and let's set both of those equations equal to 0. Our goal then is to solve these equations individually for m and b. You'll notice that the 2 from the previous slide is missing from each of these terms, but there was in fact a 2 on each of the addends inside the sum. So because I'm setting things equal to 0 here, I could factor a 2 out of each of these sums, and in fact I could factor the 2 out of the whole big summation and say that the only way for 2 times this sum to be equal to 0 is for this sum to be equal to 0. So if you're wondering where the 2's went, we factored them out and we canceled them away. Overall, between these two equations, they're both a little bit frightening, but in general, this one on the bottom seems a little less frightening to me than this one. Looks a little bit shorter and looks a little bit simpler. So what I'm going to do is I'm going to start toying around with this equation, and I'm going to see if I can solve it explicitly for my variable b. Once I've done that, I can take that b value, I can plug it into this equation to eliminate the variable b, and hopefully, with what's left, I'll be able to solve for m, and then I'll have the m and b values that minimize my residual sum of squares function.